Okay, in the last lecture we have discussed about the sequential circuit design and then its behavioral modeling of the sequential circuits. So, we have discussed the circuit diagram of a sequence detector which can detect 3 or more ones in a bit stream. Okay. So, we have written the Verilog code using behavioral modeling. So, because of this circuit complexity, sometimes it becomes difficult to write the Verilog code. So, we can directly write the Verilog code from the state diagram. Okay. For the complex systems whose state diagrams are complicated, so we can directly draw the Verilog code using the state diagrams. Okay. Today, we will discuss how to write the Verilog code using the state diagram or FSM. I will call as HDL modeling using FSM or state diagram. I will take the same example of the sequence detector. Which can detect 3 or more consecutive ones in a bit stream. Okay. So, we know the state diagram of this one is we have 4 states. S0 output is 0, S1 output is 0, S2 output is 0, S3 output is 1. Okay. So, if it receives 0, it will stay here itself. This label represent input. If the input is 1, it will go to the next state because it has to detect 3 or more consecutive ones. Similarly, here if a 0 is received, so it will go to again the reset state which is S0. If a 1 is received, it will go to the next state. Here if a 0 is received, it will go to S0. 1 is received, it will go to the next state. Here 0 is received, it will go to the S0 state. 1 is received, it will stay itself because already detected 3. So, this circuit can detect 3 or more consecutive ones. Okay. So, this is the state diagram or FSM we have discussed in the last lecture. But in the last lecture, using this FSM, we have designed the sequential circuit using flip flops, and then we modeled the flip flop based circuit using Verilog. Okay. Whereas, here we can directly model this FSM, so that the Verilog code becomes somewhat simpler. Okay. So, how to write the Verilog code in terms of the FSM? So, module sequence detector output and also register we will call as Y. I will write all inside this one also. This is also another way to represent input output. Instead of writing again separately this input outputs, I will write here itself. So, there will be only one output which is called Y and one input X, another input is clock. I am going to use another input called reset. Here no need to again define this register, the output and input. Okay. Now, here I am assuming that this S0 is reset state. That is, whenever this sequence detector circuit receives a reset which is active low signal. So, reset bar means negative edge. whenever this becomes 0, if it is high, then it will goes to the low, this is at negative edge. So, this sequence detector automatically will goes to the state S naught. This is what is called the reset state. Whenever reset bar is 0, so this state diagram will assume the state S0, that is what is called the reset state. Okay, that is why I am using another signal reset. I am assuming that clock is positive edge triggered. And reset is negative edge triggered. So, we are going to define these states with binary values, okay, using a statement called parameter. Parameter is the keyword used to assign some binary values to the states. Okay. So, here I am using S0 is equal to 2 binary 0 0, S1 is equal to 2 binary 0 1, S2 is equal to 2 binary 1 0, S3 is equal to 2 binary 1 1 semicolon. This is how to write after the parameter, okay, here. So, we are going to define some constant binary values to the states using this parameter keyword. Okay. Now, always at positive edge of clock or negative edge of reset, we have to define state, current state and next state. So, we can have a register here, register 1 is to 0, state comma next state. So, always at positive edge or negative edge of the reset, if reset is equal to 0, if reset is equal to 0, the initial state is equal to S0. Else case, now we have 4 different values of this state. So, this state is 2 bit value, because this is 2 bit 1 0. So, state 1, state 0, state 0 is LSB, state 1 is MSB. Okay. So, we have already defined S0, these are x, this is represent x, this represent x. So, when the state diagram is in state S0, when the input is 0, it will go to the S0 itself, when input is equal to 1, it will goes to S1 state. If this is true, then the next state is equal to S1, else next state is equal to S0 itself. Okay. If x is equal to 1, if this is true, next state is 1. If x is equal to 1, the next state for this S0 is S1. If false, it will remain in the S0 state only. Okay. Similarly, for S1, if x for S1 0, it will go to S0 state, 1 it will go to S2 state. So, if this is true, next state is equal to S2, else next state is equal to S0. Okay. Similarly, S2 if x, next state at S2, 0 means next state is S0 itself. If true, next state is S3, else next state S0, S3 if x, next state is S3 itself. In S3, if the input is 1, it will go to S3 itself, else next state is S0. So, this is about the description of the state diagram. Then what about the output? In S3 state only output is equal to 0. You can see that S0 we have output is 0, S1 output is 0, S2 also output is 0. Only for S3 we have output is equal to 1. Okay. So, for that you can write end case, this case is over, assign output y, we have called the output as y is equal to S3 equal to 1. Means whenever S3 is equal to 1, this is true, y is will get y, okay. Y is equal to 1 or state is equal to, you can write. So, y is equal to state, if the state is S3, if this is true, state is equal to S3, if this is true, y is equal to 1, otherwise y is equal to 0, okay. End module. So, this is about this Verilog code using FSM. Okay. You can see that this code is very simple when compared with the code which we have written for the sequential circuit which we have implemented using JK flip flops. Okay. So, this is about this sequence detector. In a similar way, you can design any sequential circuits, all the synchronous counters. So, for that matter, any synchronous sequential circuit can be designed in the similar manner. So, using the procedure that we have described in the last lecture. Okay. This is one of the important sequential circuit. So, basically sequential circuits means normally we will deal with the counters and shift registers. Okay. So, the next sequential circuit is shift register. As the name implies, so upon the application of this clock, the contents of the register will be either shifted to the left or right. Okay. Depends upon whether the content shift to left or right, it is called as shift left register or shift right register. Okay. So, before going for the shift register, if you see basically a register first of all. What is register? It is a group of flip flops which stores the binary information. So, normally this flip flop that we are going to use is D, because in case of shift registers we want to transfer the data from input to output. So, D flip flop is very much suitable for the shift registers. So, we know that each flip flop can store 1 bit of the information. So, if we want to store n bits of the information, we require n flip flops. So, if you connect all these n flip flops together, it can store n bits of the data. Okay. So, in general a n bit register consisting of n flip flops. Okay. If I consider a 4 bit register, it will have 4 flip flops. This is D0 LSB flip flop, this is Q0 output of the LSB flip flop, D1 Q1 Q1 bar, D2 Q2 Q2 bar, D3 Q3 Q3 bar, and all these flip flop will be having some clock, either it can be positive edge triggered or negative edge triggered, even it can be level triggered also, because in D flip flop there is no problem with race around. So, if you want to store any data, you can directly load the data at this point. Suppose if I want to feed a data of 1011, so you take here 1 0 1 1, you just apply the clock signal, then this data will be feed here, means this will be 1 will be available here, 0 will be available here, 1 will be available here, another 1 will be available here. So, this will continue until the next clock signal is applied, whether it can be positive edge triggered or negative edge triggered. Let us assume that all are this is positive edge triggered. So, till the next positive edge is applied, so this data will be stored. Okay. If I do not apply this positive edge, this will be present as long as the power supply is there. That is how we can store the data. But in many applications it is required to shift the data either to the left or right. Okay, if we take a binary number, if I shift the data to the right, okay, it will divide by 2, if we shift to the left it will multiply by 2. So, like that multiplication division operations also can be performed. So, in addition to that, there are a lot of applications where we require to shift the data of the register. Okay. So, this is a simple 4 bit register without any options of shifting the data to the right or left. Now, I will slowly move on to the shift register. Say first I will take 4 bit shift right register. If you want to shift the data to the right, what you have to do is, circuit diagram is same, we have to use 4 D flip flops, but the connections are different. This is D3, D2, D1, D0. Correspondingly, the outputs are Q0, Q0 bar, Q1, Q1 complement, Q2, Q2 complement, Q3, Q3 complement. Here the data that has to be fed has to be given here. This is called MSB in, and the data from Q3 will shift to D2, Q2 to D1, Q1 to D0, and this will be lost, this data will be lost. So, you see the circuit diagram of a 4 bit, and this will be having common clock, if I assume that this is positive edge, this is common clock. This is the circuit diagram of 4 bit shift right register. If you want to explain the operation, So, we can write Q3, Q2, Q1, Q0. So, here if the data that is to be feed here is say 1 is the first bit, 0 second bit, 1 1 and so on. Okay. So, initially let us assume that, so in when clock is equal to 0, initial state is 0 0 0 0. How to establish this initial state? Using preset and clear inputs. Okay. Now, if I apply the first clock signal and if the first bit of MSB is 1, whatever this 1 will be transferred to the Q3. So, this 1 will be transferred here, whereas this is shift right, as the name implies, this Q3 will shift to Q2, Q2 to Q1, Q1 to Q0 and Q0 will be lost. So, this 0 will shift here, this 0 will shift here, this 0 will shift here, this 0 will be lost. At the second clock signal, the second bit that is applied as MSB in will be inputted into Q3, 0, this 1 will be shifted here, this 0 will be shifted here, this 0 will be shifted here, this will be lost. At third clock signal, the third bit is say 1. So, this 1 and this 0 will be shifted here, this 1 will be shifted here, this 0 will be shifted here and this will be lost. At fourth clock signal, if I assume that the fourth bit is 1, this 1 will be shifted here, this 0 will be shifted here, this 1 will be shifted here. So, you can see here this will be lost. Now, you can see here this 1 0 1 1 0 1, whatever you have taken here, this bit is 1 1 0 1. This will be feed into the register after 4 clock cycles. Then if you want to take this data, we are feeding this data serially, this is called serial in. You want to take the serial data out, serial out. If you apply 4 more clock signals, if I apply 5th clock signal, this 1 will be outputted here. At 6th clock signal, this 0 will be outputted. 7th, this 1 will be outputted. 8th, this 1 will be outputted. So, after 8 clock signals, what happens? Whatever this data we have fed serially, that will be outputted serially. Okay. So, this type of register can also be called as serial in, serial out register. Okay. If I want the serial in parallel out, then 4 clock cycles are required. After 4 clock cycles, if I read the data from here, so what will be the data available? Is whatever that you have fed serially is 1 1 0 1. Okay. So, if you want to convert the serial in data into parallel out, we require 4 clock cycles in case of 4 bit shift register. In general, for n bit shift right register, to convert the serial in data into parallel out, we require n clock cycles, whereas for serial in, serial out, we require 2n clock cycles. Okay. So, see about the shift right register. So, in shift right register, so what is D3? D3 is MSB in, D2 is Q3, D1 is Q2, you can see here D2 is Q3, D1 is Q2, D0 is Q1. So, these are the binary expressions for 4 bit shift right register. In a similar manner, you can implement shift left register also. 4 bit shift left register. Now, here the serial in will be at LSB. Okay. So, here this is D0, at D0 we have to feed the external data which is called as LSB in, or we can also call it as serial in. Then this is Q0, Q0 complement, this Q0 is connected to D1, this is Q1, Q1 complement, this Q1 is connected to D2, this is Q2, Q2 complement, and this Q2 is connected to D3, this is Q3, Q3 bar. We can take the data serial out from Q3. Okay. We can explain the operation in a similar manner. Similarly, if you want to take the parallel data, you can take from these 4 points, this is parallel out. So, we can perform 3 operations here. Similarly, in previous case also we can perform 3 operations. One is serial in, serial out. So, how many clock cycles are required? As we have discussed in the earlier circuit. So, for serial in, serial out, we require 4 clock cycles. In general, for n bit, n clock cycles. Sorry, this is 8 clock cycles. Whereas for serial in, parallel out, 4 clock cycles. Now, other 2 options are parallel in, serial out, parallel in, parallel out. How to input the data parallelly? Okay. For that, you can use preset and clear signals also, or we can directly feed onto the Ds. Here I will show using preset and clear. If I make all preset values to 1, this is preset values, this is clear values. So, we know that preset operation when q is equal to 0, this is called clear operation. This can be obtained if clear bar is equal to 0, preset bar is equal to 1, and preset operation q is equal to 1 if clear bar is equal to 1, preset bar is equal to 0. Suppose if I want to feed the data parallelly 1 0 1 0, say 1 0 1 0. So, these 2 are 1s, means this preset is 0, this preset is 0. So, that 1 will be transferred, this preset is 1, this preset is 1. Whereas, the clears, these 2 has to be 0, this is 0, this is 0, and these 2 are 1s. Then automatically this data will feed. So, for parallel in, to input the data parallelly, we require only 1 clock cycle. To get the serial data, we have to apply 4 clock cycles, so that this 1 0 1 0 whatever you have fed here 1 0 1 0, to take this from here out, we require 4 clock cycles. After first clock cycle, this will be out, second clock cycle this will be out, third clock cycle this will be out, fourth clock cycle this will be out. Okay. So, we require total 4 clock cycles. Because this preset and clear are there are asynchronous inputs, they does not require any clock cycle. We can feed this 1 0 1 0 simultaneously without clock by making corresponding preset and clears 0 or 1. Okay. So, parallel in, if want to input the data parallelly, we do not require any clock cycle. Okay. To take serial out, we require 4 clock cycles. For parallel in, parallel out, this does not require any clock cycle. Once if you feed this, if you read from this Q3, Q2, Q1, Q0, you will get, so whatever you have feed 1 0 1 0 will be available here. Okay. The CIO can perform 4 operations. One is serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. Okay. This is about shift left and shift right registers and with parallel load. Now, if I want to combine all those things, shift right operation, shift left operation, parallel load operation in a single shift register, that is called universal shift register. Here I am going to perform 4 operations. Okay. 4 operations means we required 2 selection signals. So, I will take the selection signals as S1, S0, then the operation. You can design in any way. So, I am designing this circuit such that 0 0 no change, whatever the state of the register remains in the previous stage only. Okay. The register remains in the previous state only. 0 1 I want to shift right, 1 0 I want to shift left, 1 1 I want to apply parallel load. So, what will be circuit diagram for this? Okay. So, because we have 4 different operations and 2 control signals, I can use a 4 by 1 multiplexer. Okay. So, basically here I am going to use 4 by 1 multiplexers. This is another 4 by 1 mux, this is another 4 by 1 mux, this is another 4 by 1 mux. So, we know that this is 0, 1, 2, 3, we have 4 inputs 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3 and 1 output. There are 2 selection signals. This I will apply S1, S0. These are common to all the 4 multiplexers. Now, what are the signals that has to be applied at 0th input of the first multiplexer, first, second and third? Similarly, here what are these 4 inputs? Similarly, for the third multiplexer, what are the 4 inputs? Fourth multiplexer, what are the 4 inputs? Who is going to decide this depends upon whether the operation is shift left or shift right, parallel load or it remains in the same state. So, basically this 4 multiplexers is going to drive 4 D flip flops. These are 4 D flip flops. with common clock signal, and you can also provide the clear signal also similar to the previous counter. You can have clear input, preset inputs are permanently tied to 1. So, if I connect this clear signal which is active low signal, this is clear, this is positive edge and this is say negative edge. So, whenever a 0 is applied, what happens, all the 4 flip flops will reset. So, we know that we have 4 flip flops with different Ds. Okay. Say this is D3, D2, D1, D0. So, this I am going to connect to outputs of the corresponding multiplexers. This output I am going to connect to D2, D3, this to D2, this to D1, this to D0, because the multiplexer will be having only one output. Okay. So, the corresponding outputs I will call as Q3, Q2, Q1, Q0. Now, to satisfy this table, so 0 0 no change. So, what should be this 0th input, 0th input, 0th input, this 0th input such that, so these 4 flip flops will remain in the previous state only. So, for that we have to apply here Q3, here Q2, here Q1, here Q0. So, whenever S1 S0 is 0 0, so this 0th will be selected. So, the output will be simply Q3, Q2, Q1, Q0. So, when input is Q3, output is also Q3. Okay. So, it will remain in the same state. Let's see how we can satisfy this condition. 0 0 no change means, so just feed this output, there is a connection from this output to this input, but I am not showing directly, I am writing Q3 Q3 because there is a, these two are shorted. Okay. Now, we can think of what will be the first input. When S1 S0 is 0 1, then this 1 inputs of all the 4 multiplexers will be selected. Now, what will be the first input? So, for shift right, I have already derived the relation. For shift right, D3 will be MSB in and D2 is Q3, Q2, Q1. So, D1 is Q2, D0 is Q1. Okay. So, MSB in Q3, Q2, Q1. So, this is the point where we have to apply MSB in, and this is the point Q3, this is Q2, this is Q1. So, this Q3 is this Q2 is this, and so on. There is a connection, so I am not showing those connections. Okay. Now, for the shift left, so I have drawn the circuit, but I have not given the expression. You can write in a similar way. So, what is D0 here? D0 is equal to LSB in, D1 is equal to Q0, D2 is equal to Q1, D3 is equal to Q2. These are the expressions for shift left register. Okay. So, D0 is LSB in, then Q0, Q1, Q2. So, this is LSB in, this bit is LSB in, and this is Q0, Q1, Q2, right. This is Q0, Q1, Q2. Now, only thing left is 1 1, S1 S0 1 1, this 3 inputs will be enabled. So, I want to use parallel load. So, whatever the data that I want to feed parallelly, I will take here. Say I will take the input as I3 bit, I will apply here. I3 can be 0 or 1. Okay. In general, I will take I3, I2, I1, I0. Okay. So, whatever the data given at I3, I2, I1, I0, and if S1 is equal to S0 is equal to 1 1, this data will be feed into the register. Okay. That is called parallel load. So, this is about the universal shift register. This can perform these 4 operations. Okay. Now, to how to write the Verilog code corresponding to this universal shift register. Okay. Module universal shift register So, what are the inputs and outputs? Inputs are S1, S0, I3, I2, I1, I0, then we have MSB in, LSB in, then clear, clock. These many inputs are there. Okay. Here 2 inputs, here 4 inputs, here 2 inputs, here 2 inputs. So, totally I have 10 inputs. And how many outputs? Outputs are finally this Q3, Q2, Q1, Q0. Okay, only 4 outputs. First I will write output register three comma 0 because vector Q comma input three comma 0 I input, and we have S1, S0, LSB in, MSB in, clear, clock. I have defined inside this parenthesis itself. Now, always at positive edge of clock or negative edge of clear. If clear is equal to 0, so clear is equal to 0, simply all the Q3, Q2, Q1, Q0 has to be stayed in 0 0 0 state. Okay. Q is equal to 4B 0 0 0 0. So, 4 bit 0 0 0 0, else you have to follow the case. So, he is going to decide S1 S0, right, S1 comma S0. So, what are the possibilities? 2B 0 0. If S1 S0 is 0 0, okay. So, what will be the outputs? No change, means outputs will be Q3, Q2, Q1, Q0. Q only. Okay. 2B 0 1, what will be Q? This is MSB in, if I follow in the MSB to LSB. What is the order? MSB in, then the second bit is Q3, Q2, Q1. This is the order we have to give. Okay. So, I will give in the same order MSB in Q3, Q2, Q1. MSB in 3:1 Q. Okay. This will assign Q to MSB in Q3, Q2, Q1. 2B10 Q, this is Q2, Q1, Q0, Q2, Q1, Q0, LSB in. So, you have to give in this order Q2, Q1, Q0 is 220 Q, Q2 Q0, Q2 Q1 Q0, comma LSB in. Two B11 is parallel load, Q has to be loaded with I. I3, I2, I1, I1. This is I3, I2, I1, I0. This I have already defined as vector here. We will write just simply I. Okay. So, end case, end module. This is the Verilog code for a universal shift register, which can perform the 4 operations. One is it remains in the same state, shift left operation, shift right operation, or we can load the parallel data. With an additional thing, whenever clear is equal to 0, the flip flop will be clear to 0 0 0 0. Okay. Okay, with this is about the shift registers. Okay. So, I will discuss about this test bench, how this can be run through this simulator, okay. How to write the test benches and all, we will discuss in the next class. Thank you.